Today we'll be learning about priority queues. So, what a priority queue is that it's a data structure that allows you to assign priority values to your inputs. And obviously, the higher the priority, the earlier the input will be taken out of the priority queue compared to, everything else. So, what does this look like? Well, for example, let's have inputs A, B, and C. And let's say A is super important, right? So we need to assign a high priority value to indicate that. So let's give A a priority value of 5, right? And let's say B is a lot less important, right? So let's give a priority value of 1. And let's say C is somewhere in between, right? So let's give it a value of 3. And now, whenever we need to extract it, right? The first one coming out of this priority queue will be A, because it has the highest priority, right? So A is coming out. And then after that, our second highest priority needs to come out, right? So we'll expect C to come out next. And then after that, B, because it's the lowest priority, and also the third highest, right? So it's coming out third. So B comes out after that. And if you look at this, it's like the order in descending, well, it's in descending order of priority, I guess. It comes out because, the highest priority one's coming first, the next highest one's coming second, and the lowest one's coming last. So, how do we implement this? Well, that's a hard question, but you can visualize it through the priority queue here. And this is a visualization of the heap implementation. And basically, what we're doing here is it's like a tree, I suppose, but instead of having everything this side be like smaller, this side be larger, the only rule here is the top one's got to be larger than the two lower ones, right? So as you may notice, 73 is in fact larger than 61 and 69. 61's larger than 51 and 15, and so forth for every single part of this tree, right? Another thing you may notice is that these ones are full, and like these ones are all completely empty, right? And that's because this tree is meant to fill up from like the leftmost side first, right? So all these top rows have got to be filled out first, and these bottom rows have to be filled out next, right? It's just a rule of how the tree works. So that might not make much sense now, right? But when we try to insert something, right? For example, v equals 5, right? We'll just insert it at the end, right? But now you might be thinking, what if we insert something like that's like really large, right? What if we wanted to insert, say, v equals 97, right? Obviously, if we just inserted it here and left it alone, that wouldn't be doing much, right? Because then obviously 97 is not broken, sorry, it's not lower than 15, it's not lower than 61, it's not lower than 73 certainly, right? So what we do here is we still insert it at the end, but then we do a series of swaps, right? So we swap it with 15 because that's larger, swap it with 61 because it's larger, and we swap it. And now you can see it's still a correct tree by now after all the swaps are done. Because 97, the biggest one's now at the top, 73 is below, and well, everything else, 61 still above 5 and 15. This side of the tree is completely correct. And well, yeah, so when we try to extract something, we'll still be extracting the largest element, right? So let's simulate extracting something, right? So in this case, we'll be deleting out 1, because obviously by extracting the largest element, we'll be taking out the 97. So let's extract that now. As you can see, we just drag the 15 up, right? So that's not left empty. And what we do is we basically swap it with the highest one of like its two, well, children, I suppose. So for example, if you wanted to look at it again, let's do another delete and maybe make it a little slower. It doesn't really matter. No, it's already at the slowest. As you can see, 74, obviously we replace it with 5, and 69 smaller than 61, so it was swapping with this side. And then 68 was larger, so it swapped with this side. And because obviously we already checked that 68 was larger when we went to like do this swap, right? 68 when it ends up on top, obviously still going to be larger than 19. And that's basically how you can think of it, right? But how we implement it is actually a bit different. Because as you may realize, our normal tree implementation with like left pointers and right pointers and etc., it's quite a lot of space, right? And as you may notice, we're only using like this much actual space. So what we can do is we can do some really annoying maths, honestly. Well, actually, it's not that complicated. So if you look at this, 4, you can see the left node here, right? Its number is 8, right? And as you notice, 1 is at the base of the tree, 2, 3, 4, 5, 6, 7 here, 8, 9. These little numbers under the tree indicate, I guess, the position they would be at if you stored them in like an array, right? So the reason we can do this, right, is because the left node is always going to be like twice the node before it, the root node, right? And the right node is always going to be that plus 1, right? Because we're only filling it up from this left side, and because we have to fill these levels out first, right? That's just how the tree works. So if you have a look at something like this, right, you can see the left node is just 2 times 4. Sorry, wait, no, it's just 2 times 2 equals to 4, right? And this left node is 4 times 2 equals to 8. And then obviously, because this one's right next to it, right? It's just that plus 1. So what people have realized is that we can just put that in an array and just have, our last thing be an array of size. Well, in this case, it'd be of size 10, because we don't use the 0. Because obviously, if we had a 0 node here, right? 0 times 2, that's still going to be 0. So yeah, that messes with the maths a fair bit. So we just don't use the 0 node because it'd be more complicated maths. So here's an example of how it works. Let's say we want to insert a value, right? This is a min heap example, right? But it's the same concept. In this case, we're going to be removing the smallest. In this case, we're removing the largest. Doesn't really matter, right? So let's add something in. So we insert 99 here, right? And as you can see, it occupies array space 1. And now if we insert something like 77, it's smaller, and then we'll swap these two, right? And we can keep going with inserting these values, and you'll see the swaps are happening. And in the array, similar swaps are also happening to represent that. So if I insert a 23 here now, you can see that it's functionally the same as swapping the left elements, because our 1 node was here, right? This is 1. This is our 2 node, and this is our 4 node, right? So what we were actually doing there was we were swapping 4 with 2, because before 123 was there, we need to switch those two around, and then we swap 2 with 1. And you can mess around with this implementation, right? So you can insert values in higher values, lower values, and it's quite similar when we remove the smallest, right? So if you remove the smallest, you'll notice we replace the node with like this value here, right? Which is just going to be the last one. So now we're going to remove smallest. As you can see, we did the swaps again, right? With the 2 node and the first node. And that's basically how we ensure that it's still balanced. I hope this was a good introduction to binary heaps and priority queues.